last time we started talking about the terrestrial planets in the solar system, and we spent a lot of time talking about the Earth, and we'll use that to give context for why the other terrestrial planets are the way that they are. We'll finish up the terrestrial planets today and then move on to the gas giants. So first we talked about why the sky was blue on the Earth. So let's see if you remember why the sky is blue. So the air molecules scatter blue light more than they do red light, and so it looks like there's blue photons coming from all different directions because of that scattered light. Okay, so the moon is not a planet, but it is a large rocky body that we can study in the solar system. There's evidence for a lot of volcanic activity on the surface of the moon about 3 billion years ago, and so that's shown in kind of the darker flat areas on the surface of the moon. So those are called maria, because when people first started looking at the moon, either with their eye or through telescopes, they thought they looked like seas or oceans, and so they called them maria. Now we know that they are old lava fields, and that's what gives them the darker color. So there was some evidence of geologic activity early on in the moon's history, but now the moon is geologically dead. But the moon is the only other place besides Earth that humans have stepped foot. Yeah, so those are the real sounds and footage from the surface of the moon. So the only other place that humans have been besides the Earth. So something that looks pretty similar to the moon is Mercury. So they're both gray, they have a lot of craters on their surface. They show past evidence of some kind of geologic activity. And so we'll use the amount of cratering that an object has to talk about how geologically active it is. So if you have a lot of craters on your surface, then you haven't had geologic activity after that impact to erode the craters away. So the moon and Mercury have a lot of craters, and so there's evidence of very little geologic activity. There's a very large impact crater called the Caloris Basin on Mercury, and so it's outlined in this white dotted circle here. So this is on one side of Mercury, and then if you look at the exact opposite side of Mercury, you'll see a bunch of cracks in the surface. So basically whatever hit Mercury was really big and had enough kinetic energy that not only did it make a big impact crater on one side, but the shock waves caused damage even on the opposite side of the planet. So lots of big impacts happening very early on in the solar system's history. There's also some evidence of some tectonic activity, and this is actually a result of the planet cooling and contracting. So when your planet forms, it's turning a lot of gravitational potential energy into heat energy, but eventually that heat is going to dissipate, and in terms of planetary geology, when something cools down, it shrinks, and so you have the crust, which was some size, and now the planet underneath of it is shrinking, and so you get these big cliffs where the planet has basically contracted. And so you see these long cliffs on the surface of Mercury, which leads us to believe that it's cooled off enough that there's no current geologic activity going on inside of Mercury. There is some evidence of some activity, but it's just minerals getting vaporized from the surface. So you get these kind of hollows dug out in the surface that aren't craters, but we think it's minerals being vaporized from the surface. And so there is activity, but it's not coming from out from the interior of the planet. It's basically the sun heating up the surface and vaporizing some minerals. So there's a lot of evidence of cratering on Mercury and the moon, which tells us that any geologic activity that there was going on, it has long since stopped. So there is some evidence of that activity from the lunar maria on the moon, and there's some tectonic activity on Mercury from shrinking when it ran out of internal heat, but basically since then it's just any impact crater that happens is going to leave its crater, and there won't be any new features going on the surface. So Mercury and the moon are dead geologically. Okay, so those are kind of the less interesting objects. So now we'll move on to Mars and Venus, which are the more interesting geologic planets. So if we compare Mars to the Earth, Mars's radius is about half of the Earth's radius, and because of the way volume works, that means it only has 10% of Earth's mass, so it's a much smaller planet than the Earth. It's a little bit farther away from the sun. It actually does have an axial tilt, so it's not rotating on its axis straight up and down, it's a little bit off to the side. And a day on Mars is about the same time as a day on the Earth. So it takes the same amount of time to spin on its axis. Mars does have a thin atmosphere, but not enough for humans, certainly. And so the big difference is that Mars is smaller. And when we talked about planet size last lecture, there were a lot of consequences to being smaller. So Mars does have an atmosphere, and there is weather on Mars. So this is two pictures comparing Mars in June and another one in September. And so in June you could see the surface, you can see craters, you can see the polar caps on Mars. But then in September there was a big dust storm blowing across the whole surface of the planet, and now you can't see anything. So there are active weather patterns on Mars. There are lots of features on the surface of Mars that lead us to believe that there was water flowing on the surface at one point, but not anymore. And there's lots of evidence for past geologic activity on the surface of Mars. And we think maybe even volcanic activity as recent as 180 million years ago. So certainly in the time frame that there was life on Earth, there was geologic activity happening on Mars. The two main features on the surface of Mars are Olympus Mons and Valles Marineris. So this is the largest volcano in the solar system, and this is a large canyon feature on Mars. And just to give you a sense of scale, the Olympus Mons would take up basically the entire state of Arizona, and Valles Marineris would be imagining the Grand Canyon spanning the whole continental United States. So these are very big geographic features. And Mars is smaller than the Earth, so these look big on the Earth. They're even bigger if you compare them to the size of Mars. We've sent a lot of rovers to the surface of Mars. So these are images from the Opportunity rover. And again, finding more evidence for past water flowing on the surface of Mars. This mineral is called hematite. And so the picture on the left is Mars. The picture on the right is Arizona. And so this mineral is typically only found where water has been flowing, particularly salty water. And so just building up more evidence that there was water on the surface of Mars in the past. Again, this is looking at the erosion patterns on the rocks on Mars, and you can see they're very rounded, and that only happens from erosion. Could it be from wind on Mars? Maybe, but we see those very rounded pebbles and stream beds on Earth, and so again, just more evidence that there was water flowing on the surface of Mars in the past. These kind of horizontal bands going through the rock are sedimentation patterns, and so that's material being deposited on top of the layer of rock by water. And so again, this is more evidence of water on the surface of Mars. Today we think there is still water on Mars, but there's not liquid water flowing on the surface. So most of the water is frozen below the surface of Mars, and this is taken from an orbiting satellite, a satellite that's orbiting Mars. And so this, we think, is water ice so this is the surface and this is a cliff face. So this is water ice that's just below the surface of Mars, and you can see it in this cliffside. So why was there water on Mars, but now there's nothing? So there has been climate change on Mars. Early on in its history, it was warmer, and so its mantle was moving. If you have charged particles in the mantle moving around the solid metallic core, you can get a magnetic field, and that magnetic field protects your atmosphere from the solar wind. So if you have a magnetic field, you can have an atmosphere, and due to the greenhouse effect, you can have a warm surface. So we think Mars had an atmosphere, or had a magnetic field in the past that led to a thicker atmosphere, that led to warmer temperatures, allowing liquid water to flow on the surface. Now Mars is much smaller than the Earth, so it didn't retain its heat as well. So its magnetic field, it no longer has a magnetic field, or at least not a very strong one. And so the solar wind has stripped away its atmosphere. Without a thick atmosphere, it's colder on the surface, and therefore you don't get a liquid water flowing on the surface. So we'll watch, maybe we'll speed this one up. So this is the landing of one of the probes on the surface of Mars. And so you have to send it there in a spaceship, and then the spaceship drops its payload. And before it gets to the surface, you have to hope your parachute and everything open up so that you can slow down and not basically destroy everything when you hit the surface. So this is the view from the probe as it's going down. So that's why the ground is getting closer and closer as time goes on. And the little pictures on the bottom show you what stage you're at. So they've already deployed their parachute, and they've dropped their heat shield, and now they've dropped some other component. Now they've dropped the rover, they've jettisoned the parachute, and now they're going to activate some thrusters to do their final landing, basically. And they drop the rover on like a little crane system so that it lands nice and softly on the surface. And then that little crane part will go land somewhere else so that it doesn't hit the rover. And then here's a video of one of the rovers driving around on the surface of Mars. So this is what Mars would look like if you were to drive on the surface. We've also launched little helicopters on the surface of Mars to do more tests. So we've sent a lot of probes to Mars, and a lot of people are excited about trying to send people to Mars too. So maybe that's something that we'll be able to see in our lifetimes. Okay, so we think there was liquid water on the surface of Mars. We see dry riverbeds. We see erosion that you get from water flowing over rocks. We saw some chemicals that we only see on Earth where water has flowed. We do think there is water in the form of ice on Mars, but it's either below the surface or at the poles. And so it might be available for humans to use, but it's not just waiting for us on the surface. Why did it go from having liquid water to having nothing? Mars used to have a thick atmosphere that was protected by a magnetic field, but as the planet cooled down, it lost the ability to have a magnetic field, and therefore its atmosphere was stripped by the solar wind. So this is what happens if you are too small and you lose your atmosphere. And The other planet, terrestrial planet that we'll talk about is Venus, and this is kind of the opposite direction. So Mars got too cold, and Venus is going to get too hot. So we'll talk about why Venus is so hot and if it's geologically active. So these are pictures taken from the surface of Venus. So these are actually Soviet probes. So the Soviet Union sent a series of probes to the surface, and they didn't last very long because it's very hot and very high pressure. But it's still very cool to see these actual pictures from the surface of a planet that humans will probably never go to. And you can see kind of the advances in technology of the cameras from one mission to the other. So you have black and white, and then you start to have color, and then you have even better definition and color in the most recent probe. So Venus has a lot of evidence of geologic activity on the surface. And remember, we can't see the surface in visible wavelength light, so these are all radio wavelength images that we are looking at. So there are some impact craters on the surface of Venus, but much fewer than we see on Mars or Mercury or the Moon. There's lots of volcanoes, so this is a twin peak volcano on the surface of Venus. There is some evidence of tectonic activity. So you can see these kinds of valleys and kind of ridges that are forming. Doesn't look like there's a lot of evidence of erosion, so this is from one of those landers, and you can see the rocks have very sharp edges, and they haven't been smoothed by liquid or wind. So we talked about tectonic activity, but that doesn't mean that Venus has plate tectonics. So on the Earth, we have our continents and oceans sitting on top of big plates that kind of float on top of the mantle, and that's responsible for a lot of our geological processes on the Earth. We don't think that Venus has those kinds of plate tectonics, but there was something happened 750 million years ago that basically, when we say repaved, we mean basically the surface became molten and erased any evidence of past cratering. So this could be a very large impact that released a bunch of energy that made a bunch of molten material come to the surface. And remember, Venus rotates on its axis in the opposite direction of all the other planets. So there had to have been some very large impact that caused that to happen. Whether that was the same impact that caused the repaving of the surface is not clear. So why is Venus so hot? It's because of the greenhouse effect. So the atmosphere of Venus is made out of mostly carbon dioxide, and that's very good at trapping heat on the surface. But why does Venus have such a strong greenhouse effect compared to the Earth? So Venus has a very thick carbon dioxide atmosphere, and the atmosphere is so thick that it causes the pressure on the surface of Venus to be 90 times that of the Earth. So we have a similar effect on the Earth. If you go underwater in the ocean, the deeper you go, the greater your pressure. So you can imagine trying to land something on the surface would be equivalent to trying to get a submersible to great depths in the ocean. And so it's very hard to do, and basically any probe you send there is going to break down very quickly. Carbon dioxide is a very strong greenhouse gas, and so it's any energy that's either coming from the interior of the planet or that's able to penetrate the clouds in the atmosphere is going to be trapped. And so all that heat is getting trapped. The surface is much too hot to have liquid water. So 470 degrees Celsius is 370 degrees Celsius too hot for you to have liquid water. The Earth has not had the same runaway greenhouse effect for reasons that we'll talk about in a little bit. There are some reflective clouds on the surface of Venus, so it's not all dark colors. There are some lighter colors that would reflect sunlight. And there are some very fast-moving winds in the upper atmosphere of Venus that remain unexplained. So if you were interested in meteorology, you could become a planetary meteorologist and study the weather patterns on Venus or Mars. So the runaway greenhouse effect on Venus, if there was liquid water on the surface, the energy from the sun is going to heat up the water vapor. The water vapor is going to become gas and go up into the atmosphere. And the more greenhouse gases you put in the atmosphere, the better you are at trapping heat. And so you get a runaway greenhouse effect that you vaporize your gas, the gas traps more heat, you vaporize more gas, you trap more heat, and so you just run away and you get no water left on the surface. On the Earth, there are some mechanisms that will take the carbon out of the atmosphere and trap it below the surface of the Earth, and that's how the Earth has so far avoided having a runaway greenhouse effect. But humanity is currently pumping greenhouse gases into the atmosphere faster than those natural processes can keep up. So what is the main reason Venus is hotter than the Earth? Yep, greenhouse effect. Okay, so we don't see any evidence for erosion or plate tectonics, but there is still debate about whether Venus is geologically active. Venus is so hot because it had a runaway greenhouse effect, and that could be a preview for the Earth if humans are not careful. Okay, so part of what we'll answer now is what processes does the Earth have that are preventing, for example, a runaway greenhouse effect? And what other features of the Earth make Earth a habitable planet? So I'll let you guys talk amongst yourselves for a couple of minutes and see what ideas you come up with for what features make Earth unique and are important for life. let's see what features we need. So the main features that we need for life on Earth: surface liquid water, atmospheric oxygen, plate tectonics, and climate stability. So the last two are going to be related to the processes that have so far prevented the Earth from having a runaway greenhouse effect. So surface liquid water, the Earth is in what's called the Goldilocks zone, so it's far enough away from the sun to have liquid water on the surface. If you're too close to the sun, your surface will be too hot, and if you're too far away from the sun, your surface will be too cold and all the water will freeze. So the Earth is just the right distance that we have liquid water on the surface. We also have lots of oxygen in the atmosphere, so photosynthesis, which is what plants do for them to live. They make O2, and they also take in some oxygen when they do their photosynthesis. When you release that O2 into the atmosphere, it will react with energy coming from the sun, and it can break the O2 into two oxygens, and then those free oxygens can merge with another O2 molecule and make an O3 molecule, which is ozone. So remember, ozone was what you needed to protect the Earth from ultraviolet radiation. And so the ultraviolet radiation can cause mutations in DNA, and so without the O2 and O3 in the atmosphere, it's going to be very hard to sustain life on the surface. Plate tectonics, so this is what's responsible for, example, the motion of continents, but it's an important step in the carbon dioxide cycle on the Earth. So that's the cycle that takes carbon out of the atmosphere and has prevented the Earth from having a runaway greenhouse effect. So these are not all of the plates on the Earth, but these are the big ones. And so you can see different continents sitting on different plates, and these plates all move with respect to each other because you can think about them floating on top of the molten material in the mantle. And so when the two plates collide, they can make mountains, and when the two plates drift apart, they can create seas and rift valleys. So, but it's not just things moving around. The plate tectonics will also take CO2 out of the atmosphere. So really, before we had the science to prove or study plate tectonics, people were curious, like, isn't it weird that South America and Africa look like they fit together like puzzle pieces? And that's because in the past they did fit together, and it's just the motion of plate tectonics that has forced them apart, and so now they're no longer touching each other. So this is that process that takes carbon out of the atmosphere and traps it under the surface of the planet. So there's all these different plates. Material from the atmosphere will rain down either onto the land or onto the ocean. If it goes to the land, it'll eventually drain into the ocean. And the heavier material, for example, containing carbon or carbon dioxide, will sink towards the bottom. The seafloor of the ocean will be subducted underneath of the continental plates. So the continental plates are lighter than the oceanic plates, and so the oceanic plates go underneath the continental plates. And all of that material that's rich in carbon dioxide is pushed down into the mantle and basically sequestered out of the atmosphere. So this is what takes carbon out of the atmosphere, or carbon dioxide out of the atmosphere, and traps it, preventing runaway greenhouse effect. Eventually that material is going to be recycled and put back into the atmosphere, but over a very long time scale. And so this kind of the evolution of what the continents looked like. Very far back in time, we think all of the land mass was connected in a supercontinent called Pangaea. Eventually, the continents have drifted apart, and what the current arrangement is not how it's going to look for forever. So, in 150 million years, if humans have not killed themselves by then, you've got Australia kind of merging with Antarctica, and Africa's coming towards the Americas, and Europe and Asia have rotated. So, some interesting things that could happen for future map makers. And so here's that carbon dioxide cycle again. So you have the CO2 coming down in the form of rain, either from hitting the land or hitting the oceans. And that material will sink towards the bottom and chemically react with rocks. Those rocks will subduct under the surface and become part of the mantle. And eventually, the material from the mantle can be brought back up to the surface in the form of volcanism. But this cycle takes a lot of carbon dioxide out of the atmosphere and prevents runaway greenhouse effect. But it's not just the planet getting too hot that you have to worry about. In the past, so this is a theory called snowball Earth, we think either the entirety of the planet or almost all of the planet was covered in ice. So during ice ages, you get a expansion of the polar caps basically towards the equator, and we think one of those periods of glaciation actually either got to the equator or very close to the equator. So when you have a surface covered in ice, ice is very reflective. So any heat that you would normally get from the sun warming up the surface is now bouncing off and going back into space. So if you don't have a mechanism to reheat the Earth, you can be stuck in basically a frozen and dead world. So this is another way that volcanic outgassing can, so the carbon dioxide cycle prevents the Earth from getting too hot, but it can also save you if the Earth gets too cold. So even though the surface is covered with ice, you're still going to get volcanic activity. That volcanic activity can outgas greenhouse gases, and if you get enough of those greenhouse gases in the atmosphere, you can heat the Earth back up and go from a period of glaciation to a period where there's not ice covering everything. And at least the way that current life works on Earth, there's a lot of species that don't want the entire surface to be covered in glaciers. So the CO2 cycle is basically a thermostat for Earth's temperature. So it prevented the runaway greenhouse effect, and it also prevents basically the Earth from becoming frozen and not being able to heat back up. And so all of these requirements are kind of intertwined. So plate tectonics are what cause the climate to be stable. The stable climate allows for liquid water on the surface. We need liquid water for ice, or for life. And then that life in the form of plants are what produced a bunch of oxygen for the atmosphere, and that oxygen turned into ozone that protects other life from harmful ultraviolet radiation. And so the distance from your star and the size of your planet are the two big factors that will determine if your planet is habitable. So you need a large enough planet, and at least for the way life works on Earth, you need it to be a rocky planet, so you have a surface for life to exist. It has to be big enough to retain enough of its initial heat to have a liquefied mantle, so you can have magnetic fields that protect your atmosphere, and it has to be the right distance from the stars so that you can have liquid water on the surface. So in a couple of weeks, we'll talk about exoplanets, which are planets around other stars, and we'll use these kinds of criteria to figure out where life could exist in other places in the universe. So Earth is habitable because it's big enough that it has geologic activity, and it's the right distance from the sun so it can have liquid water. We think Venus is either currently geologically active or was until very recently geologically active. Mars might have been geologically active up to about 180 million years ago, and the Moon and Mercury have not been geologically active for a long time. And we can use the cratering on the surface to figure that out. So if you have a lot of impact craters on your surface, then there hasn't been any geologic activity to erase those craters. But if you have a very few number of surface craters, then you've had geologic activity that's either eroded them, or you had volcanic activity fill in all those craters with magma. And so we use cratering to determine geologic activity. So what do we need on the Earth for life? Water, oxygen, plate tectonics, and climate stability. And so when we look out in our own solar system and at other solar systems, these are the things we're looking for to find life that's like Earth life. But we have to be careful with our own planet. We're releasing a lot of carbon dioxide into the atmosphere, and the carbon dioxide cycle on the Earth can only work so efficiently, and we're currently putting too much carbon dioxide in the atmosphere, and not enough of it is being taken out of the atmosphere, and so the surface of the Earth is heating up.